start it as quickly as possible. Lovely. What we're trying to do, we're going to say, let us create a mechanism to visualize graphs, simple diagrams. So we want to draw y equal to x. If you understand, I want to take for granted that we're going to know a little bit of coordinate geometry. This x-axis is y-axis. Looking to draw the graph y equal to x. So y equal to x, 0, 0 will be a point, 1, 1 will be a point, 2, 2 will be a point, 3, 3 will be a point. Very simple. Y equal to x is a nice straight line. Don't worry, this class is not going to be this easy. We're going to amp it up. We're going to say, hey, y equal to x, that we have drawn. It's a nice line. It passes through the origin, we've drawn it straight. Nice, quite simple. So, say, what else can we do? Y equal to minus x. Y equal to minus x. This is y equal to x. This is y equal to minus x. It's a beautiful idea. Y equal to x, y equal to minus x. This is a positive sloping line. This is a negative sloping line. Positive sloping line. What do we mean by that? What is the slope exactly? Slope is nothing but rate of change. And so what we say, conceptually, what is slope? We know y equal to mx plus c, we know tan theta, all of that. Y2 minus y1 by x2 minus x1. All form-like ways of understanding slope, we are all very comfortable. Conceptual way of understanding slope is very important. Right? We graph so that we can understand relations better. So don't think of it as x-axis and y-axis. Think of it as something here and something here. I've heard this idea that we generally have an independent variable and a dependent variable. Whatever is independent is put on the x-axis. Whatever is dependent is put on the y-axis. So we can say, hey, I put a number of hours of study here, and the marks you're likely to get. More hours we study, chances are the marks will be better. The independent variable here, dependent variable here. Number of ice creams I eat, and the amount of fun I have. Ice creams here, fun here. Right? So number of special classes I attend, and how irritated I am. X-axis, y-axis. Independent variable, what we can understand, dependent variable, what this drives. Whenever we do this, and so whenever we think about independent variable and dependent variable, what we want to get at essentially, whenever we are making decisions is, hey, one more unit of independent variable, what happens to my dependent variable? I am studying for 4 hours a day. If I have to take it to 5 hours a day, I'm sacrificing a lot to go to 5 hours a day. On 1 more hour of study, my marks better spike up. If after doing all this I get half a mark more, not worth my while. 4 hours a day, this 90 marks is fine for me. I don't want to spend 5 hours a day and get 90 and a half. But if it can go from 90 to 98, I'm jumping in. At 5th hour is meaningful. And so I want to take my day-to-day decisions based on that one more of x. What does it drive my? How does it drive my mind? Is it positive? Is it negative? Is it heavily positive? Is it mildly positive? I want to get a sense of one more unit of x. What does it do to y? That is the idea of slope, the notion of slope. Super powerful idea. Very often, whenever we are discussing slope, we think of y1 minus y2 by x1 minus x2. We could think of y equal to mx plus c. We could think of tan theta, the imaginary angle, all of that. But funda-wise, there's an independent variable, and based on this happens. I'm continuously taking a lot of my life decisions based on, if I do one more unit of this, what do I get? I have one more ice cream, how much fun do I have? I have one more ice cream, how much more trouble I am in with my father? Is the trouble worth the joy? I always take this decision. If I play football for 20 minutes more, my father is going to scream at me. I'm going to come late and be a pain. But that 20 minutes gives me a lot of joy. So is the joy more than this? Is the slope of joy is greater than the negative slope of what I'll get when I go back home. So I can always take this decision, multiple graphs. What is the input, or what is my independent variable? My dependent variable. Super powerful idea. Why I tell you? Because I go next and say, hey, draw y equal to x, y equal to 2x, y equal to 3x. Y equal to x is like this, 2x, like this, 3x. The slope becomes steeper, 3x. You will change x by 1 unit. Y will change by 3 units. One more idli, I'm getting so much joy. One more ice cream, I'm having so much fun. Powerful. You suppose it's something that you don't really enjoy. And one more could give you only 0.1 more units. Low slope, high slope. Steep slope, slope is higher. Nice, simple. Y equal to minus 5. This is y equal to minus 5. Minus 5. More variance in y vis-a-vis change in x. But when x increases, y decreases because I have a negative slope. When x increases, y also increases, my slope is positive. When x increases, y decreases, my slope is negative. Super important idea because this really is the bedrock of understanding a lot of calculus. And very often, we do so many things with slope without having a sufficient grasp of what it is that is slope. At that point, if I change x by 1, how much does y change by? We take all our life decisions based on this. Is it worth going 5 minutes late? If my train is at 9 o'clock, will I game the system to get 10 more minutes in front of the TV and look to reach at 8:40? Or is my pain point with potential tension so high that I'll say, chuck this TV, I'll be there at 8:30? Taking all these decisions based on weird graphs in our head, based on 10 more minutes of TV, how much joy, how much anxiety. For some, the anxiety about reaching is so high, the joy gets clouded. For some, the joy is so thrilling that they shut off the anxiety and then get in trouble every now and then. Right? So, all of us have different graphs every time we take decisions. We're all taking decisions on the increment and doing one more unit of this. I'm sure all of you thought about this and said, look, I'm going to attend this class today because it's going to be massively useful, super fun. What am I sacrificing? I'm not able to watch the 10th episode of nice sitcom I had. I can chat something on Instagram. I could do something on YouTube. I can watch the IPL match. So my 1 hour extra spent on this, the positive curves I'm getting here, the negatives I'm losing there. If the positive offsets the negative, then I'm going there. Otherwise, I'm not. And so the notion of slope, the power of slope is super important. But we're not going to stop with that. Let's build on this. Y equal to 5x. Y equal to 5x plus 4. Y equal to 5x is a line like this. Nice? Forget the number, I'm drawing freehand, right? So don't look at this point and say maybe that's not 5x, that's 4.8x. Forget about that. Just y equal to 5x. But my question says y equal to 5x plus 4. So it's like amount of happiness with number of hours of beautiful classes learned. It could be y equal to 5x, more classes I attend, I'm fine. Or it could be y equal to 5x plus 4. What does that mean? If I had no classes, I'm still happy. 4 units of happiness is guaranteed. My starting point is 4 units of happiness. Whether I attend class or not, I'm happy. If I attend 1 more hour of class, I'll get 5 more units of happiness. But my position of starting is with happiness. Y equal to 5x plus 4. That even when x is 0, y is 4. Or this graph shift it up. Take it up. Move to the side. Drag it up. That is this line. Y equal to 5 plus 4. Y equal to minus 3x plus 5. Y equal to minus 3x is like this. Minus 3x plus 5 is like this. If you say y equal to something, and then instead of that, it is plus 5, then I'm taking this graph and pulling it upwards. Every point that I have line, what it was originally, it will get 5 added. I take this and drag it up. I take this and I drag it up. That's what I'm doing. Right? Lovely, we've got the basic outline done. I hope, I'm just looking for something on the chat screen. Nothing so far. We've just begun this thing. I'm going to draw a bunch of graphs and charts. If you have questions, please put them on the comment thing. If you have tech issues, forget about it. Manage with the tech. This is the tech we have. You're not going to get better tech than this. So forget about the tech. Right? Lovely. I'm going to go to the next set of ideas. Y equal to 5x plus 4 minus 3x plus 5. We draw both of these graphs. Where they meet is that set of points where this is satisfied and this is satisfied. Solve the equation. And that solution that we get is the point here. Basics of coordinate geometry. All the points on this line. If I get x coordinate and y coordinate, if I substitute x coordinate as x, y coordinate as y, this equation should be satisfied. This one, this line, red line is 5x plus 4, black line is minus 3x plus 5. All the points in this line satisfy one equation, this line satisfies that one equation. The meeting point, that point satisfies both equations. How do I find the meeting point? Solve these two equations, find x, find y. That set of values of x and y satisfies both equations, or that point sits on this line and this line, or that is the point of intersection of the two lines. Lovely, beautiful. Raghu is saying all good. Anand Gupta is saying please use another mic. And I'm going to do one more change. I'm going to keep this mic even closer and kind of scream out. He's saying the volume is too low. I'm going to see if I can give it some gain. Quality seems to be decent. Let me see if the gain plays a role. Hello. Aradhya Krishna Natarajan, can the slope change at every point? That's a question. For a straight line, no. But there are graphs for which there's a different slope at different points. And so, if you change x by 1, how much does y change by? For a straight line, it's always the same. But for different curves, it will be different at different points. Nice, lovely. Risha Kumar is saying, please try to use this. Nice. Anand Gupta is saying, I will manage. I have amped up the volume. I have amped up the volume at which I am speaking. And I have indeed given it some gain. So all three we have done. So amped up the volume and gain in two different places. Relocated the mic, that's one thing. And I'm speaking louder. It should be that little bit better. Right? Lovely. Much better. Thanks, Anand. That's a big boost. Super. This is a beautiful, beautiful idea. Right? Suppose we have a curve, a graph like this. So this is equal to y equal to f of x. This is a graph f of x. Beautifully important idea. Suppose I say I want to find f of x plus 5. I've already seen this. It is like I'm saying y equal to 5x. What is yx plus 4 or 5x plus 5? It's like I take this curve and drag it upwards. I drag it upwards. I can take this and go up. Y equal to f of x. Y is f of x plus 5. Suppose I want to not take it up, I want to take it down. Down by 5 units. Y equal to f of x minus 5. Nice, simple. Plus 5, we drag it up. Minus 5, we take it down. Done. I want to take it to the right. Why not? I want to take it to the right. Why? I've dragged it up, I've dragged it down. I want to take it to the right. If I want to take it to the right by 5 units, then x minus 5. Think about this. F of 1. If I put in this graph, if I put x equal to 6, 6 minus 5 is 1. I'll be back to f of 1. But at the point where it is 6, that is where f of 1 will be. So this f of 5 is here. F of 10, 10 minus 5 will have the exact same value. It's like saying, I have a diagram. I want to drag it to the right by 5 units. If this is f of x, this should be f of x minus 5. If I want to take it up, I have f of x. I should do f of x plus 5. I want to push it down, I have f of x. I have to do f of x minus 5. Now take it to the left, I have f of x. I'll have to draw f of x plus 5. Brilliant, fine, brilliant ideas. Super powerful. And so you've got to understand that this is going to help us draw x minus 2 whole square. It's going to help us draw x square minus 8. It's going to help us draw modulus of x minus 2 plus 3. All of that, if you know one function, you can do 5 other variants of that. Super important. Raghu was very insistent that we have this. And it's a beautiful idea here. Suppose h of x comma y is some function. G of x comma y is this. This depicts some beautiful shape, some complicated, fancy sounding thing. Now, if I have f of h of x comma y, x square plus y square equal to 3. suppose I want to, if I draw h of x minus 5 comma y minus 3, what does that become? G of x comma y is this giant thing. If I draw g of x minus 4 comma y minus 10, what does that become? That's what we're trying to get in. It's super important to say, I've got one idea, one shape in one place. If I have to move it up or down or left or right, what do I do? Super important. Square plus y square equal to the graph. If this is h of x comma y, if I do h of x minus 20 comma y plus 10, x goes to x minus 20, it will move to the right. Y plus 10, it will move down. I'll have this. If h of x comma y is this curve, h of x minus 20 comma y plus 10 is this curve. Super important. The idea of moving a graph from one place to another. The g of x comma y is this one. G of x minus 20 comma y minus 10. X minus 20 to the right by 20 units. Y minus 10 upwards by 10 units. So y gets replaced by y minus 10. X gets replaced by x minus 20. Okay. Then this curve, which is beautiful, wonderful curve. I'm sure all of you know this shape, shifts to the right by 20 units and to the top by 10 units. So any graph, you can transition it from one location to another by changing the variable. It's a super powerful idea and very often it's overlooked. And so which is why we are used to thinking about understanding a circle equation as x square plus y square equal to 25 or x minus 3 the whole square plus y minus 4 the whole square is 25. You understand that? We're doing x minus 3 the whole square plus y minus 4 the whole square is 25. We know center and radius. We can think of it as x square plus y square is 25 circle, and then I shift it by 3 units this side, 4 units this side, I get a new circle. X minus 3 whole square or y minus 4 whole square, or my center, which was at the origin, is now at 3, 4. So if you understand one graph, then a variant of that graph which is pushed away, that much easier to graph. And super important idea. Lovely. Negative sign shifts to the right, negative sign in the y shifts up. And very important, very subtle difference. If this is h of x comma y, this is h of x comma x minus 20 comma y plus 10. I'm writing the whole thing as a function of x and y. However, if we had written this, or we do a draw differentiate. Suppose I say, this is p of x. This will be p of x plus 6 going up by 6. And so, slightly different ways of treating. This h of x comma y, this h of x minus 20 comma y plus 10. I'm shifting x, replacing x with x minus 20, y with y plus 10. That is one way of thinking about it. But generally in graphs, we are given y equal to 3x minus 5x cubed. Y is given as f of x, and y is f of x plus 6. We can take the graph higher, dragging it higher. Minus 6, take it down. And so, this plus and minus don't get confused with two ways of thinking about it. We do this very clearly. Clear all this. Suppose we have y equal to x square plus 2x. I have y equal to x square plus 2x plus 5. That means I have this x square plus 2x, some shape, some curve. I'm dragging it up by 5 units. Another way of thinking about it is, I can say y minus 5 equals x square plus 2x. I have a curve which is y is something, y minus 5 is that thing, that means I'm taking it up by 5 units. If I replace y by y minus 5, I have to move the graph by 5 units upwards. One way of thinking about it. I have y is some expression, instead of that I'm adding 5, that means I'm dragging it up by 5 units. So don't get confused with this plus 5 and minus 5. Y replaced by y minus 5, my graph is going up by 5. Y is f of x. Suppose I find f of x plus 5, then my graph is going up by 5 units. The funda needs to be clear. Don't just go with plus and minus. And so approach it with the funda. Radhikrishan, positive is downwards, negative sign shifts to the right. Correct? If I'm replacing x by x minus 10, I'm shifting the whole graph by 10 units. I'm replacing y by y minus 5. I'm shifting the whole graph up by 5 units. Suppose I'm saying y is f of x, and then I want to draw y is f of x plus 5. Then I'm dragging the graph by 5 units. Y equal to f of x, y equal to f of x plus 5. I'm taking the graph up 5 units. Right? Y minus 5 is equal to f of x, and y equal to f of x plus 5 are both same. And so don't go with just a plus and a minus. Y equal to f of x plus 5 or y minus 5 is equal to f of x are both same. I'm dragging the graph up 5 units. Nice. Nice. Brilliant. There's one more toolkit which Raghu has very kindly given me. A beautiful. I'm going to do this and then go to the toolkit. The toolkit is like a big review of the thing that you can have a lot of fun with. Before we go there, there's a standard question, that's a brilliant question. Mod x plus mod y equal to 4. Find the area enclosed by this curve. And mod x plus mod y equal to 4. I'm sure all of you know what mod x means. Mod x plus mod y equal to 4. Mod x is modulus of x, plus modulus of 3 is 3, modulus of minus 3 is also 3. How do I find it? How do I draw this curve? Standard rule, put x equal to 0, find y. Put y equal to 0, find x. Put x equal to 0, mod y is 4, y could be plus 4 or minus 4. So I have 0, 4, 0, minus 4. These two are points on the curve. Put y equal to 0, x mod x is 4, x could be 4 or minus 4. Mod x plus mod y equal to 4, if x and y are both positive, mod x is x, mod y is y, and both are positive, I'm practically drawing x plus y equal to 4. Where are both x and y positive? First quadrant. Then we say nice. It is mod x that we are dealing with. If some 2, 2 works, then definitely minus 2, 2 will also work. Mod x is 2, could be 2, minus 2 will work. Minus 2, minus 2 will work. 2, minus 2 will work. If this point works, then this point will work. This point will work. This point will work. Be positive. Very interesting. How is this whole curve going to look like? Slowly, over time, you'll be able to grab this and say this. This is very algebraically, but this is a shape. It's not the point. It's not the point I'm trying to make here. You draw this curve. It will probably take you 4, 5, 6 minutes to draw this completely. And then I want to find area of the shape. Check, this is square. This is 2, this is 4, this is 4, this is 4 root 2. This is 4 root 2, this is 4 root 2. I can find area as 4 root 2 into 4 root 2. So this is a complicated, nice process. Assume you've got this. If you've not got this, spend 5 minutes, 7 minutes, you'll get this. It's not rocket science. That is not the point I want to make. This is a solvable question. This seems like a very tough question. Modulus of x minus 3 plus modulus of y plus 6 is equal to 4. Now I've drawn all this. Then I should say modulus of x minus 3 plus modulus of y plus 6 is equal to 4. What is the area enclosed by that curve? The same as this. Why? What I'm doing, modulus of x minus 3, shift x, this whole thing to the right by 3 units. Modulus of y plus 6, shift it down by 6 units. It's going to be some curve here. Centered around 3, minus 6. What will be the area? It's the same square. Push down by 3. Push to the right by 3. Push down by 6. This, I'm shifting it like this and pushing it down. What will be my area? My area will be the same. So if you're solving to find the area enclosed by the curve, you're given this question. You should say, look, this question is too complicated. I want only area enclosed by the curve. I'm going to forget this, solve for this, much easier. So if I'm shifting the curve, the idea of shifting a curve to the right, to the left, up and down, super powerful, and something that you need to get a handle. Nice, lovely. So now I'm going to do the other side of this one, rather brilliantly done. Take this. So, what you say, this is a beautiful tool. So, Raghu is really the doyen in this tool, really the king of this but I'm sure several of you have heard about this. Those of you who have not heard about this, I'm going to tell you that this is going to be a good use of 45-50 minutes that you have, probably hours that you have. You can just go to testmonster.com and then say, hey, y equal to 5x. You get the graph. Then you can say y equal to y equal to 5x plus 3. See what I do. Y equal to 5x plus 3. And then you say, look, very interesting, I'm going to draw one more. Y equal to 2x minus 7. Draw one more graph. You want to do one more. You can say y equal to minus 4x plus 5. Of course, you have to do it without typos. So, you're done with this, then you want to say y equal to x squared. You could just type in functions and it draws graphs. This is super powerful as a tool because you can just say, look, I want to have fun with this. I want to understand how graphs work. I want to understand how diagrams work. I want to understand how x is like this, 2x is a sharper slope, 3x is even sharper, 5x is even sharper. 5x plus 3 is same as dragging it upwards. 5 times x minus 2 is like dragging it to the right. Understanding that is super powerful. So whenever you're learning graph, every now and then switch off and say, I'm going to go and have a play with testmodels. Whenever you're visualizing stuff, you're going to say, okay, this is fun, but I'm going to see it in testmodels. I'm going to see how this graph appears. I'm going to see how I can visualize this. Understanding shapes, understanding circles, curves, quadratic expressions, modulus, x, linear equations, understanding them algebraically is one part of the jigsaw. Understanding them graphically, that's the real deal. And then when you understand that the graphical part and the algebraic part are linked, are connected, joined at the hip, you can see one and write the other. You can write one and see the graph in your head. Then you're through. Then you're rolling and enjoying coordinate geometry. You want to see everything, not algebraically, but visually. Right? Lovely. I'm not done. I'm going to stop with this. We're going to say, hey, nice. Later, we did the groundwork. Let's do more. Y equal to 2 times x minus 3. Beautiful diagram. I know y equal to 2 times x. I know that graph. Good friend of mine. And so y equal to 2 times x is a graph like this. Y equal to 2 times x is a graph like this. Y is 2x. I can say y is 2 times x minus 3. What does that mean? Instead of x, I put x minus 3. What does that bring? Boil down to taking this graph, shifting it to the right by 3 units. Okay? Instead of here, we go here. Nice. So I have y equal to 2x. Then I can think of y equal to 2 times x minus 3. Not y equal to 2x. 2 times x minus 3, just shift it to the right. And I'm parallel to this. Now, I'm going to reimagine this. Okay. Y equal to 2 times x minus 3 can be written as y equal to 2x minus 6. I know how that is done. Y equal to 2x I know. 2x minus 6, I just push it down by 6 units. We take this graph, push it down by 6 units. You have y equal to 2x. Move it to the right by 3 units. Throughout, we'll get y equal to 2 times x minus 3. Push it down by 6 units. We'll get y equals 2x minus 6. The nice thing to imagine is if I have this line, if I take this line and push it to the right by 3 units, or push it down by 6 units, I'm doing the same thing. Pushing this to the right by 3 units, or pushing it down by 6 units, I'm doing the same thing. I can imagine this as 2 times x minus 3, or 2x minus 6. Both are same. Pushing a straight line pushing this straight line to the right by 3 units, or pushing it down by 6 units, I'm achieving the same objective, same end objective. A beautiful way of understanding pushing to the right, pushing up, down, pushing up, that motion. Nice. So far so good. Enjoy this. In linear equations, horizontal and vertical shifts are interchangeable. Shifting to the right, shifting down, both the same. I'm going to take a mini time out here. Any questions you have, fire away. We'll discuss them and we'll go to the next set of ideas. And those of you who are curious about Desmos, go open, have a play. You learn this much coordinate geometry in an hour and a half of fooling around with Desmos than an hour and a half of anything else, than in 4 hours of anything else. And so the whole power in coordinate geometry is to say, hey, I understand shapes, I understand algebra. How great would it be to take shapes, give an algebraic link to each shape, and then do several things with them? Where do a straight line and a circle intersect, or solve the equation, get the intersection point? Where do a straight line and circle intersect? Draw the circle, draw the straight line, see where they are. And so, see where they hit. So, seeing what is happening and algebraically solving what is happening, we can marry the two in your home and learning. Ariman Pandit is saying the last part, please. We have y equal to 2x. Shifting it to the right by 3 units gives us y equal to 2 times x minus 3. Instead of x, we have x minus 3. Shifting it down by 6 units gives us y equal to 2x minus 6. Both are same. Take the straight line, push it to the right, or push it down by 6, you're getting the same straight line. Right? Sorry. Lovely. That Raghu was about to tell me something. Feel good. Lovely. You're good to go. I'm going to build on this. X minus y into x plus y is 0. It's a tough equation, right? So x minus y into x plus y is 0. X square minus y square is 0. How do we even imagine this? And how do we draw this diagram? Product of two things is 0. Then one of them is 0. Or the other is 0. Or both are 0. We know this. So either x equal to y or x equal to minus y. Either y equal to x or y equal to minus x. Or when will this happen? Y equal to x. All points on this line will satisfy this. Y equal to minus x. All points on this line will satisfy this. So y, x minus y into x plus y is 0. Nothing but saying y equal to either x or y equal to minus x. Either this line or this line. Another way of thinking about it is to say y square equal to x square, or mod y equal to mod x. Y equal to x, y equal to minus x in different ranges. And so, beautiful idea. I can break this into y equal to x and y equal to minus x and draw that. Or I can think of it as x square minus y square is 0, x square equal to y square, mod y equal to mod x, and draw that, imagine that. Nothing. We've spoken about mod x as if we understand mod x really well, as if mod x were a good friend of ours. I want to build on that. And what is y equal to mod x? Y equal to x, I understand. Y equal to mod x, there are 2-3 ways of thinking about it. And the first way is to say y equal to mod x, y cannot be negative. Y simply cannot be negative. Y is mod x. Mod x cannot be negative. Whether x is positive or negative, y cannot be negative. So first idea I have is completely y cannot be here. That only has to be there, the first and second quadrants. When x is positive, y equal to mod x is nothing but y equal to x. When x is negative, if x is minus 1, modulus of minus 1 is 1. When x is minus 2, modulus of minus 2 is 2. X is minus 3, modulus of minus 3 is 3, minus 4 is 4. Or, if you think about it, the graph like this. Y equal to mod x. Y equal to x. The graph like this. Y equal to mod x. The graph like this. From y equal to x to y equal to mod x, how do I go? Wherever the graph is positive, I retain it. Wherever the graph becomes negative, I take its mirror image. Because y cannot be minus 2. Y will have to be plus 2. And so y equal to mod x is a graph like this. Okay. Nice, wonderful. So I've drawn this curve. Now x equal to mod y. When will that happen? X equal to mod y. Now x cannot be negative. When y is positive, I is positive. Y x equal to mod y. That is, y can be negative, x cannot be negative. Mod x minus mod y equal to 0. Mod x equal to mod y. That is, draw. This will come, and this will come. The whole range will come. So mod x equal to mod y. I am drawing y equal to mod x. I am drawing y equal to minus mod x. Y equal to mod x. Y equal to minus mod x. All of these. And so it's not such an easy graph to grab. Every time we draw this, you have to do a couple of more things. You have to say, okay, I'm going to substitute a bunch of values and see if this works. I'm going to go over to Desmos and substitute the graph, substitute values and see how it works. Draw the graph, visualize it, see. Super, I'm going to build on this. Mod x, how will it be? Nice. Let's do one more. Modulus of x plus 5. Beautiful. Modulus of x we have drawn. Modulus of x plus 5. Instead of x, I have x plus 5 or x minus minus 5. And it's like saying I move the graph to the left by 5 units. Y equal to mod x is a graph like this. Modulus of x plus 5. When x is minus 5, it is supposed to see. Here. This is y is mod x. This is y equal to modulus of x plus 5. Modulus of x plus 5. Take this mod x, shift it to the left by 5 units. Getting a couple of questions on mod x equal to mod y. I'll come back to that. And then come here. Mod x equal to mod y. What am I drawing? I'm going to draw y equal to mod x. That is this. I say y equal to mod x. Whenever x is 2, y is 2. Whenever x is minus 2, y is 2. Whenever x is 5, y is 5. X is minus 5, y is 5. Drawn that. Well, to this, I'll add y equal to minus of mod x. Why? Because I'm only worried about mod y. If y equal to 2 works, y equal to minus 2 will also work. So if mod y equal to mod x, I can break it as, let me draw y equal to mod x. And let me draw y equal to minus mod x. If y equal to one value works, y is minus of that value will also work. Because I'm finally dealing only with mod y. This is y equal to mod x. This is y equal to minus mod x. Both put together we're talking about mod y equal to mod x. And so y equal to mod x is this b. Y equal to minus mod x is the inverted b. Mod y equal to mod x is both put together. Y can be mod x, y can be minus mod x. Both put together is mod y equal to mod x. That's what it's. Lovely. I'm going to go here. Mod x is this. Modulus of x plus 5 is the shift. Nice, brilliant. Modulus of x minus 5 is mod x. X minus 5. I have y equal to f of x. Y equal to f of x minus 5. Take this graph, shift it to the right by 5 units. Take this, shift it like this by 5 units. So when x is 5, y will go to 0. Modulus of x minus 5. 5 minus 5 is 0. Modulus of 0 is 0. Obviously, we're not going to say we crack this, we leave it at that. We complicate it. We complicate that little bit. Modulus of 6, x plus 6 plus 2, x plus 6 minus 2. This is minus x. This will be y equal to modulus of x plus 6 plus 2. Maybe we have minus 2. Nice. If I got y equal to mod x, I can find y equal to modulus of x minus 5, x minus 3, x plus 2, x plus 6. I've got modulus of y equal to modulus of x plus 6. I can do modulus of x plus 6 plus 2 minus 2. Plus 2, take it higher. minus 2, take it over down. Modulus of x minus 5, shift it to the right. Modulus of x plus 5, shift it to the left. Nice, wonderful. Right. Now what am I going to do? I'm going to do this whole thing a little bit more. I'm going to attack this with Desmos. I draw this also. Modulus of x minus 4 plus 2, modulus of x minus 4 minus 2. X minus 4 is this. This is y equal to modulus of x minus 4. Modulus of x minus 4 plus 2. Okay, nice. Interesting. Strongly urge you to not worry about the, don't worry about the detail. Don't say this line goes through this point, that point is not actually satisfying. I'm drawing it roughly, approximately. I want the visual idea to be embedded. The computation part we can worry about later. Visual idea is super important. Lovely. This is the most important. Modulus of x minus 4 minus 2. Beautiful idea. Modulus of x minus 4 minus 2. And so think about that. Take your time. Draw this. I want all of you to see this. This. All of these we have done. I want to take a draw and see and imagine each of them, and then say, hey, I'm going to draw this. And so spend some time, have a go at it. Right? What am I going to do? I'm going to go to Desmos. There. Excuse me. What do we want to do? We want to do modulus of x minus 4, modulus of x minus 4 minus 2. So we want to take this graph and take modulus of that. Think about what does modulus do. Modulus gives out a positive value. So you've got to think about the entire graph and say, hey, modulus of x minus 4 minus 2 is this value. Modulus of x minus 4 minus 2 is 8. What will be modulus of that? It will also be 8. It is 10. It will also be 10. It is 2. Modulus of 2 is also 2. So, if you think about this, whenever modulus of x minus 2, modulus of x minus 4 minus 2, whenever it is positive, I'm nice, I'm a very happy guy. Modulus of x minus 4 minus 2 is a graph like this. Whenever this is positive, modulus of that will remain the same. Suppose I am saying y is mod x. Whenever x is positive, it's just y is x. Only when x becomes negative do I have to worry. So one thing I can sense is when I am drawing this modulus of x minus 4 minus 2, in this part, there is no change. Whenever the y is positive, I put one more modulus around it, how does it matter? It won't matter. Y is, if modulus of x minus 4 minus 2 is 3, modulus of that is also 3. If modulus of x minus 4 minus 2 is 17.3, modulus of that is also 17.3. This part won't change. Where will the funny thing happen? Here. When my modulus of x minus 4 minus 2 is minus 1, modulus of x by 4 minus 2 will become plus 1. Here is where the funny thing will happen. That part where the original graph there is negative territory, there I'll have to worry about it. Wherever it is positive, I won't have to worry about it. And so I want some of you to crack it. What am I trying to say here? I want you to figure it out and then give me the diagram. Give me the shape of the diagram of modulus of x minus 4 minus 2. Give me some word to describe the shape of that diagram. Modulus of x minus 4 minus 2 is this. What is modulus of x minus 4 minus 2? Think about it. Give me that answer. Give me what that shape will look like. What is that beautiful thing that defines that shape? How does that shape look like? It's a nice word I want you to pick. Nice letter that I want you to pick and say, hey, it is going to be shaped like this. It is going to be shaped like batsman's wings. Up and down both, Shaksham Rajput says, Risha Kumari is spot on. Kumari is spot on. That's the letter we are looking for. We will get a W. We have a shape. I'm going to go to Desmos and see if we can draw this. Y equals modulus of x minus 4 minus 1. Something seems to be funny here. I'm going to draw this diagram. Done right there. Modulus of x minus 4 minus 2. Don't worry. We have the diagram. Maybe I think all of you have said W. That is correct. I'm going to go back to my picture here. For some reason, I'm not able to plug it into Desmos the way I want to. The shape would be like this. It's a W. Brilliant. Y equal to modulus of x minus 4 minus 2. Whole thing under modulus. That's what we're looking at. Lovely. W shape is what we're looking for. Brilliant. Quite a few of you have got it right. Just wonderful. Let's build on this. Draw modulus of 2x minus 4. This is modulus of 2x shifted to the right by 4 units. Modulus of 2x will be a graph like this. Very much like a V. Modulus of 2x minus 4. This is going to be, imagine this as modulus of 2 times x minus 2. I'm replacing x by x minus 2. We shift it to the right by 2 units, not 4 units. If you are thinking of modulus of 2x minus 4, that's different from modulus of 2x minus 4. Modulus of 2x minus 4, shifted to the right by 2 units. Shifted, you can think of mod 2x minus 4, it is shifted down by 4 units. So this is modulus of 2 times x minus 2, shifted to the right by 2 units. And so, shifted to the right by 2 units, not 4. What am I replacing x with? Instead of x, I put x minus 2. I shift to the right by 2 units. Lovely. Let's complicate this whole thing a little bit more. Even a odd function will come to this. I'm going to put this. Y equal to x square. It's a beautiful idea. What are we doing on time? We're doing completely fine on time. We have lots of time. I don't want to spend more time on quadratic equation. Let's attack this. Right? I hope the volume is clear. I hope I'm loud enough and you're able to grab everything I'm saying. Y equal to x square. Y equal to x, we know. It's a straight line. Y equal to x square will fly away. X is 1, y is 1. X is 2, y is 4. X is 3, y is 9. X is 4, y is 16. When X increases, Y increases. But Y doesn't gently increase, it flies. X goes as 1, 2, 3, 4, Y goes as 1, 4, 9, 16. It flies. Right? So this will be a curve. It just takes off and goes to and flies away. Beautiful idea. When Y equal to X square goes like this. The second part of understanding Y equal to X square is when X is in negative, Y will still be positive. Plus 1 square is 1, minus 1 square is also 1. Plus 5 square is 25, minus 5 whole square is also 25. Or Y equal to X square. This side and this side will be symmetric. I'm having Y equal to X square on both sides. Looking symmetric about the Y-axis. And it's not a gentle straight line thing, it's something that flies away. It just goes, takes off. Brilliant. Now, let's see what else we can add. Y equal to minus X square. That's easy to imagine. This is Y equal to X square. This will be Y equal to minus X square. Whatever X value, X square we get, minus of that. Go down. Instead of 1, we'll have minus 1. Instead of 2, we'll have minus 2. Just take a mirror image that we've got. Y equal to X square we've got. Y equal to minus X square we can get. Nice. Aradhya Krishnan saying, could we go over the last bit once again? We'll come back. We'll come back and cover some of these modulus bits all over again. Okay? X equal to Y square, how will it be? X equal to minus Y square, how will it be? Same, whenever we get Y equal to X square, X equal to Y square, just to reimagine X axis and Y axis, flip them. So X equal to Y square, X cannot be negative, symmetric like this. X equal to minus Y square. Put X equal to Y square and X equal to minus Y square, we'll get an X. So X equal to Y square looks like this. X equal to minus Y square looks like this. Y equal to X square is a U. Y equal to minus X square is a U. Nice, so far so good. Let's go, let's keep doing it. Y equal to X cube. X bar 4 will be X bar 5, how will it be? I'm going to start with X square. X cube. X square goes as 1, 4, 9, 16. X cube goes as 1, 8, 27, 64. It will fly. X bar 4 will fly. X bar 5 will fly. Just take off and fly. Fly like this. All of this. Start. X square, X cube, X bar 4. Other interesting thing, Y equal to X square, this side and this side give me a remaining. X cube can become negative. I'll draw all three different colors to this properly. Square, square. Cube, cube. Square would fly, X cube will fly even more, X bar 4 will fly even more. When I say fly, I mean for a small change in X value, there will be a giant change in Y value. Y value will just take off, higher powers. X square and X bar 4 never become negative, X cube can become negative. And understanding these shapes is important, just to get a sense of how much they fly away, how fast they fly. And so how much the X square thing takes off is super important. Nice. Oh, this is the most interesting part. Right? So Y equal to X square, we know how to do this. From this, right? Obviously assume there's a nice symmetric shape and all that. Right? So we've got that. What is Y equal to X minus 2 the whole square? Instead of X, I have X x minus 2. What will I do? Take this graph and say, hey, nice. This is a y equal to x minus 2 whole square. Nice, so far so good. So x minus 2 whole square minus 6. What will that be? Take this and say, hey, nice. Push it down. Take this, push it down. This is x minus 2 whole square. This is x minus 2 whole square minus 6. Y equal to x square, y equal to x minus 2 whole square, y equal to x minus 2 whole square minus 6. Whole graph gets pushed down. My graph is not looking too good. I'm going to see if we can erase this one. Redraw it. So here, video. Y equal to x square, I have x minus 2 whole square shifted to the right. X minus 2 whole square minus 6 is pushed down. Which is nice because I want to expand this. What is this? This is x square minus 4x plus 4 minus 6. X square minus 4x minus 2. Suppose you're asked to draw x square minus 4x minus 2. How do we draw this? You say, hey, nice, interesting. I think of this as x minus 2 whole square minus 6. Draw that. I know how to draw x square. I know how to draw x minus 2 whole square. I know how to draw x minus 2 whole square minus 6. X square, x minus 2 whole square, x minus 2 whole square minus 6. And through. Okay. Lovely. So every time you draw a quadratic expression, break that, reimagine that as a square, completion of square, as a square and something remaining. Don't think of it as x square minus 4x minus 2. Think of it as x square minus 4x plus 4 minus 6. X minus 2 whole square minus 6. And get through. Brilliant. Let's see. Hang on this. So this is x minus 2 whole square minus 6. Now if you think about it, beautifully, I'm having this expression. I can say y equal to x square minus 4x minus 2. Where does it cut the x-axis? Cut it from there here. Cut it from there here. How do I find that? I find that by saying, putting y equal to 0. Or, if I'm dealing with x square minus 2x minus 4x minus 2 equal to 0. X square minus 4x minus 2 equal to 0. If I take that equation and solve it by putting it equal to 0, I will get two real roots. Here and here. If I take y equal to x minus 2 whole square equal to 0 and put my discriminant and find out that, I'll get only one real root. I'll get two equal real roots here. Y equal to x square, roots are 0, 0. Yeah. So our quadratic equation solving idea, by saying completion of squares and simplifying, and the visual representation of that can be linked. And super important, right? Let's build on this. Obviously, let's build on this. Y equal to x square minus 2x plus 4. How do you do this? So I want to draw y equal to x square minus 2x plus 4. Okay. Draw this, give it some shape, tell me how it will look like. Text form, find the words. Say it will be U shape, it will be umbrella shape, it will be like a lying down U, it will be like a big, it will look like an M, it will look like a W, it will look like a K, it will be a U that is floating in the air, it's a U that cuts the x-axis, it's a U that bottoms at x equal to minus 3. Give me something to describe this, draw this, see. So spend some time thinking about it. Y equal to x square minus 2x plus. I know how to draw y equal to x square. I know how I draw x square plus 3. X square minus 2x plus 4. I know how to draw x minus 1 the whole square, x plus 3 the whole square, all of that I know. I'm going to look at this and say, reimagine this as y equal to x square minus 2x plus something. Plus something. What is this plus something plus something? This should be the number that makes this an x plus k the whole square. I know x plus k the whole square is x square plus 2kx plus k square. Minus 2x here. I put 1 here. Out of the 4, 1 has been accounted for, remaining is 3. format. This can be thought of as x minus 1 the whole square plus 3. Brilliant, I'm through. I know y equal to x square is a curve like this. X minus 1 the whole square is a curve like this. Here, x minus 1 whole square plus 3 will be a u that is floating above the x-axis, bottoming out at a point x equal to 1, where y happens to be 3. I can describe it like that. X square I know, x minus 1 whole square I know, x minus 1 whole square plus 3. The beauty about this, the point where we understand this clearly, we take this quadratic expression and I say I do my quadratic equation part and do the discriminant part and find out what roots it has. It will come out as saying it has no real roots. Why? This curve never cuts the x-axis. This curve never has a scenario where y equals to 0. If I put y equal to 0 and solve for it, I will not get any real roots. For no real value of x, thus y equal to 0. So any quadratic expression that has no roots will not cut the x-axis anywhere. It has two real roots that are distinct. It will cut the x-axis at 2 points. It has one root or two equal roots. It just touch the x-axis. And so understanding quadratic expressions as some x minus k the whole square plus p is super important, super powerful. Once you do that, we can draw the graph. Nice. Alpha max, the answer is correct. The description is correct. Spot on. So minus 6x square plus x plus 5. So we draw this very interesting, very tough, very challenging. I don't want to draw, I don't understand minus 6x square. I would say this is minus of 6x square minus x minus 5. It's tough. So we have minus 6 outside. So x square minus x by 6 minus 5 by 6. It's an x by 6 sitting there. So I can have 1 by 3 whole square, 1 by 12 whole square, becoming 1 by 6. 1 by 12 into 2 is 1 by 6. You can imagine this as minus 6 times x minus 1 by 12 the whole square and a congestion term. X minus 1 by 12 will have 1 by 144 with it, and then a minus 1 by 144 with it, and then I simplify it and reimagine it. And so I'm not going to do the whole process. Instead of that, I'm going to make my life simpler. Go here, close this, and draw y equal to x square, and then y equal to minus 6 square. I want to be minus 6 square, and then go here and put minus 6x square. We have minus 6x square plus x plus 5. Minus 6x square plus x plus 5. It's an inverted u. Peaks close to the value x is little more than 0, where y becomes little more than 5. We can algebraically complete the square, find the value, simplify it. We can visualize it using Desmos like the graph. Perfect, alpha max, perfect. At x equal to 1 by 12, it peaks and it's a parabola inverted u with the peak close to x equal to 1 by 12. I can imagine this as 1 by 12 minus x minus 1 by 12 the whole square, something minus x minus 1 by 12. 5 plus 1 by 144 minus x minus 1 by 12 the whole square. That's what this expression will be. So at 1 by 12, it peaks. You can simplify and modify the equation like that. Lovely. 9x square plus 12x plus 4. How do I simplify this? First of all, I take the 9 out. Then say x square plus 12 by 9x plus 4 by 9. If I can draw this, I can draw this. I just multiply everything by 9. Make everything bigger. I know x square plus 12 by 9x. 12 by 9x should be 2 times something. 6 by 9 the whole square. Forget this, deal with only this. X square plus 12 by 9x plus 6 by 9 the whole square minus 6 by 9 whole square plus 4. This I know is x plus 6 by 9 the whole square. 6 by 9 the whole square is 36 by 81 plus 4 by 9 plus again 36 by 81. Nicely breaks down this expression, nothing but x plus 6 by 9 the whole square. So at x equal to minus 6 by 9, it goes to 0. Minus 6 by 9, it goes to 0. Complete the square, deal with the remaining part, get the square, the thing to be a parabola or an inverted parabola with the peak or bottom at that point. X plus 6 by 9 the whole square and then an adjusting term, no adjusting term in this case. At x equal to minus 6 by 9 it will hit 0. Grab that and get. Alpha max again spot on upward parabola, vertex at minus 2 by 3 comma 0. Minus 6 by 9 is minus 2 by 3 comma 0. Lovely. So if you look at this, a curve like this has discriminant negative, no real roots. A curve like this has discriminant positive, 2 distinct real roots. A curve like this has discriminant 0, 2 equal real roots. You complete the square and see what is remaining. When we think about discriminant, we link the idea of the graph with the discriminant idea and the completion of squares idea. So that rounding off and visualizing curve is super important. So do we ignore the 9? No, we don't ignore the 9. So without that 9, this curve would have been, how do we describe this? Y is more powerful. Each point will be lower. Let's visualize this on test mouse. This is y equal to x square. This is y equal to 5x square. At each point, instead of 1, it will be 5. Bigger, the y value of magnitude higher. This is y equal to x square. This is y equal to 5x square. At each point, the magnitude is higher. So it just gets more power at each point. How should I find out the intersecting point in the x-axis in the previous question? Put y equal to 0, you'll get the intersecting point in the x-axis. Nothing else. Let's answer the question from Prita Selvam. Aradhya question, do we ignore the 9? No, we don't ignore the 9. Also, what do we do with the negative sign in the first part? So if you're drawing, very simply, let's do this. This mouse is super powerful, let's use this. X minus 2 the whole square. Minus of x minus 2 the whole square. So if you can draw x square minus 4x plus 4, we can draw minus x square plus 4x minus 4. Draw for easier thing that we can imagine. And then the minus is just a flip of it. This is a parabola like this, minus will be just a flip of it, inverse. So if you're drawing minus 7x square plus 14x minus 19, take out the minus, keep it aside, deal with the remaining. complete the square, take the coefficient, complete the square, deal with it, then put the coefficient, make it powerful, put the minus, reverse it. Step-by-step process, but the negative coefficient of x square forms an inverted parabola always. Perfect. That's from alpha max. That is correct. So if coefficient of x square is negative, you're going to get a curve like this. Coefficient of x square is positive, you're going to get a curve like this. Where it cuts the x-axis, does it cut the x-axis at all? That's separate. And so this can be higher or lower. If a coefficient of x square is positive, then you get a u. If coefficient of x square is negative, you get a number. Lovely. I think we're pretty much done. Nice, this goes nice. Minus of x minus 1 whole square plus 2 and x minus 2 whole square plus 1. This function is defined as the minimum of these two. Beautiful question. I think it's an excellent question. And so, whenever you're given questions like this, you typically told solve the equation, equate the two, find the answer. So, we're going to visualize this. So, this minus of x minus 1 whole square plus 2, this part is going to be a curve like this. X minus 2 whole square plus 1 will be a curve like this. We're going to draw both of these curves and then see them. X minus 1 whole square, when x is 1, this goes to 0, plus 2, so when x is 1, this goes to 2. This curve, at x is 1, this goes to 2, when x is 1, this will be 2. Inverted parabola, when x is 0, it will be 1 square minus 1 whole square, 1 plus 2. When x is 0, this is 1 square, 2 minus 1, when x is 0, y will be 1. When x is 2, y will be the curve. And this one, x minus 2 whole square plus 1, when x is 2, this will be minimum. When x is 2, this will be minimum. And the minimum value will be 1. When x is 1, this will be 2. So this is the curve. One is an inverted view, other is a normal view. Beautiful. Now comes the most interesting part. The function is the minimum of these two. So if I draw a function graph, and whenever x is these values, this side, this will be the graph up to here. And then at this point, in this range, this will become the graph. Why? That is higher than this. Beyond this, this will be the graph. So minimum of these two, draw the first curve, draw the second curve, look at both curves. Whichever curve is lower at each point, that's what we've got to graph. Here, this curve is lower, that curve is higher. And this stretch, the U curve is lower. In the final stretch, the inverted U curve is lower. So this is how this graph is. All good, brilliant. Where will it be? Where is the maximum of f of x at this point? Quite simply, we are asked to solve for this and find this. What will we do? We'll find a point of intersection. Where are these two equal? Be equal from 2 points. Find the functional value at 2 points. Whichever one is maximum, that's your answer. Suppose I'm given this question in the exam. What am I doing? I'm saying minus of x minus 1 whole square plus 2 is equal to x minus 2 whole square plus 1. You need two values of x. What will be the two values? This and this. X equal to 1, x equal to 2 or 2 point something, depending on what the value is. For both, I'll find functional value. Whichever one is higher, that's my answer. So just equate these two, solve for x, get the two meeting points, find f of x1 and x2, the two meeting points, okay? Whichever is higher, that's my maximum value. That's what I'll do algebraically, mechanically. What is happening is the curve will happen to be like this. Where will it be maximum? At the point the two curves intersect. Where do the two curves intersect? At 2 points, here and here. Where will be maximum? Wherever the functional value is higher among the 2 points, which is this point, theta. But sitting inside the algebraic method, equate the two, solve for x, find functional value, is this curve. One is a u, other is an inverted u. You want to find the function is the minimum of these two, which is this. The function curve is going to be like this. What is the maximum point of that function? How do I find out point of intersection of the next point? Prika Selva, can you repeat this one? Lovely. I'm going to erase the whole thing. Let's start all over again. X minus 1 minus of x minus 1 whole square plus 2. So here the coefficient of x square is going to be negative. I'm going to have an inverted u. Where will my peak be? The peak will be when x is, this part is 0 and x is 1. For this curve, put x equal to 1. 1 minus 1 whole square is 0. Y will be 2. This will be my peak, which is 1 comma 2. Nice. And then it will be a parabola. It will be an inverted u. The maximum is here. It will be a third. Not drawn to scale with accuracy and all that, but I get it. Then I'm going to say, very nice, very interesting. We draw this curve. Where will its bottom be? Minimum. X equal to 2. When x is 2, what is y? Y equal to 1. X minus 2 whole square goes to 0. Plus 1. 2 comma 1. 2 comma 1 here. That will be the bottom. This will be a u on the bottom here. What do we say? Hey, nice. Got the two curves. What is my function? My function is said to be minimum of these two curves. I imagine my function. Say, suppose for my function, if I put x equal to minus 1, then when x is minus 1, this gives a value, and this gives this value. What value will my function take? The lesser of the two, because it's minimum of these two. So if I look at it visually, the lower curve is what I'll occupy. What is the lower curve here? The blue curve. So my blue curve will be the relevant curve till here. And then from this stretch to this stretch, from this point to this point, my red curve is lower. After this blue curve is again blue. So my functional graph will be this one. What am I going to do? I'm going to say knife. I'm going to erase this. This is all my functional graph. Brilliant. I got my functional graph. Now I want the maximum value of x, which is this point. How do I find it? This point happen to be nothing but point of intersection of my blue curve and red curve. Nice. So I'll find blue curve and red curve and see where they meet. When I see where they meet, will I get only this point? No. I'll get this point and this point. I'll take both of those points and say, one of these is my answer. I'll find functional value and two meeting points. Whichever one the functional value is higher, that's my answer. That's the algebraic way of doing it. What is happening graphically, what is really happening is this. Lovely. Lovely. I think I'm coming up onto a close of this lovely class. I don't think we have too much more left. The McDonald's graph. What Raghu wants you guys to do with Desmos, with hanging around with Desmos, is say, hey, plot this. Figure out a way to plot this. Figure out a way to plot this. Not just shifting in my mind. Figure out a way to plot this. Figure out a way to plot this. Drawing these graphs, carve out the McDonald's. So, mathematically, draw the McDonald's symbol is what Raghu wants you to do. Go to Desmos and then plug in these shapes. Maybe this is a, maybe let's say this point is minus 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, minus 2, 10. So this is an inverted graph. So should have x square coefficient to be negative. Peaking at x is minus 2, or should be minus of x plus 2 whole square plus 10. X equal to minus 2 will give us 10. That is this curve. Then draw this curve. Then draw this curve. Then draw this curve. Then figure out a way to not have this curve all the way through. Just stop there. Otherwise, it will be one weird shape with too many parabolas out there. And then draw this McDonald shape. Super tough project. Incredibly tough project. And so, try that. Reach out to us. We're always happy to help. Go to Desmos, have a play. And then enjoy ourselves. I want to kind of stop with that. If you have any questions, come back. The visual idea of questions of finding maximum, minimum, seeing where it cuts the x-axis, where it cuts the y-axis, how many roots are there, when does x go to 0, when does y go to 0, how do we imagine x minus 2 whole square plus 7. Those are super crucial. Several exams just get unlocked. If you can think of an algebraic expression visually rather than algebraically. And so you can even say, hey, how will this graph look? Let's do this. Desmos. X minus 1 into x minus 2 into x minus 1 into x plus 3. The roots are 2, 1 and minus 3. Greater than 3 will be positive and fly away. Less than 2 will be negative and collapse. Sorry, less than minus 3. Greater than 2 will fly away and be positive. Less than minus 3 will be negative and collapse. It goes to 0 in these three places. It will bottom out interim here, peak out to the interim here, and be like this. So, cubic equation, you can plot that one. So, plug in values, have a play, understand where a graph will be positive, where it will be negative, where it will be 0. Suppose you're saying beautiful curves here. So, let's say modulus of x minus 4 plus modulus of x minus 6. You see that, see how it plays out. Between 4 and 6 there will be no difference. Outside of that, it will fly. Expand it. Just try different values and have some fun playing with it more than anything else. If you do a ton of things on Desmos and enjoy yourself drawing these graphs, you go to the visual link of coordinate geometry is going to come in place. Right? So, here, parabola, hyperbola. So we'll first start with fooling around with straight lines, then maybe circles, then quadratic equations, then we can go to hyperbola, parabola, ellipse, quadratic equation, parabola, effectively. All of that. And then the more you see the visual representation compellingly, the more sound the understanding of this whole topic becomes. Right? I'm going to stop with that. Quite lovely interacting with all of you. Please do comment and say, hey, what else we can add, what are the shapes you can add. If you have a mechanism where you've drawn a graph and put beautiful shape, you just copy that graph thing and stick it in the comments. We'll put it in Desmos and see how it works. One of my pet peeves about learning coordinate geometry, especially the Indian way, is coordinate geometry is this powerful tool that links geometry and algebra, visual shapes and x's and y's, diagrams with equations. Okay? Very rapidly we are taught to go to the equation world. Where does a circle intersect with a straight line? Substitute an equation in a circle, solve for x. There are two roots and it's a chord. If there's no root, then it doesn't touch. There's only one root is a tangent. Just go pa 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 pa. You want to find the slope of the tangent, differentiate with respect to x. What is differentiation? What is slope? What is the idea of rate of change? How is x square plus y square equal to 6? The same as x minus 2 whole square plus y minus 4 whole square equal to 6 in a different place. That idea of visualizing shapes just goes out. ellipse is a beautiful idea. Sum of the distances to 2 points is a constant. It's a very powerful idea. Tracing the path of the ellipse, imagining the ellipse, seeing the ellipse, very powerful. And somehow in our Indian system, we solve this much, you see this much. I want you guys to stick a pin on that and say, look, I will solve, I'll get to the solving part, but I'm going to see as much as possible. The more you see and learn, visualize in the coordinate geometry, the better your grasp of why coordinate geometry is there. I quite enjoyed myself. Desmos also provides some very fun graphs to play with. Now, the Batman graph is this. So, obviously, it goes without saying, I didn't draw this. So, you give all this as a clue, then you can draw the Batman graph. And then quite beautifully, you haven't taught me how to do this. I'm going to try this. Put x minus, k equal to x minus 4, you shift Batman to the right. You put m equal to y minus 5, you take Batman higher. You can make Batman rotate about that. You can make Batman go around the circle. You can make Batman bounce up and down. You can make Batman move to the left and right. So several things you can do. Once you have drawn the Batman equation, which luckily enough for us, now is done. And then you can move Batman up and down, left and right. You can make Batman bounce. You can make Batman shift. You can make Batman go around a circle, rotate about a point, all kinds of things. Right? So the possibilities are endless. In terms of kind of having fun with Desmos, definitely do that. The whole class is our effort to say, learn coordinate geometry visually, don't learn it merely algebraically. Algebra is like this gun we have, where we can do magical things in coordinate geometry by just manipulating x and y. One of my professors used to say, coordinate geometry is the ugly tool to solve geometry questions. I'll tell you why. Let's do this. Finish the class, I'll do some breaking down. Just trying to find a place where we have some more place. And so there's a beautiful idea in geometry that says the medians of a triangle are concurrent. They meet at a point. And they meet at this point called as a centroid. So, there's an incredibly tough proof. You draw this diagram, draw this. And then you say, hey, I can imagine I can do A, B, C. And then you draw a line like this. And then establish some similar triangles ideas. And then prove that the centroid, the three medians are concurrent. When they meet at the centroid divides the median to the ratio 2:1. Beautifully rigorous, challenging, tough, thorough understanding of geometry. Or you can just say, hey, this is x1, y1, this is x2, y2, this is x3, y3. This point is x2 plus x3 by 2, comma y2 plus y3 by 2. Take these 2 points, divide in the ratio 2:1, find this coordinate. Take these 2, divide in the ratio 2:1, find that coordinate. Take these 2, divide in the ratio 2:1, find that coordinate. Establish that all three give us same x1 plus x2 plus x3 by 3, y1 plus y2 plus y3 by 3. Celebrate same. The point that divides each of the medians in the ratio 2:1 is the same point. So the three medians must meet. Under the meeting point, the centroid divides the median in the ratio 2:1. Easy proof. It's taking all kinds of powerful geometric ideas and pandas and similarity, winning it, and saying I'll brute force my way out of this. Other way you can do is x1, y1 to x2 plus x3 by 2, y2 plus y3 by 2. I can draw the straight line equation. Define the straight line equation. Solve that. Find the point of intersection. From this to this point of intersection, find the equation of the line and establish that x1 plus x2 by 2, y1 plus y2 by 2 lies on that. Again proving that the point of intersection of two medians happens to lie on the third median, or the three medians are concurrent. Then you can find the point of intersection, and then you can do section formula and establish that it is 2:2. Quite If you do this, you should get a medal of honor. It's incredibly tough, incredibly painful to form the equation of a point line joining x1 y1 and x2 plus x3 by 2 comma y2 plus y3 by 2. You will get a weird, unhappy equation. And this, and then solve those two by cross multiplying and eliminating one variable. And then find the point of interest, which will deliciously come out to x1 plus x2 plus x3 by 3, comma y1 plus y2 plus y3 by 3. We are not done yet. We just found the point of interest, two medians. Now we take the third median equation, substitute this, it will work. That means this point lies on the third equation. So all three are concurrent. We are not done yet. We take the median and then say what ratio it divides this line in. It will happen to be 2:1 for all three median, therefore 2. And so take one mathematical geometric idea, take all intuition out of it, dive into the algebraic world and solve. That's both the beauty of coordinate geometry and the really ugly side of coordinate geometry. And so I want to make sure that you guys can see the power of coordinate geometry. Coordinate geometry turbocharges your geometry. It can. If you get stuck somewhere, you can brute force your way out of trouble. The three orthocenters, the three altitudes are concurrent. x1, y1, x2, y2, x3, y3. Slope of this line. It's -1 by that. Define that line. Define this line. Find the point of intersection. Draw the third one. Extend it. That will happen to be perpendicular. And three altitudes are concurrent. They meet at orthocenter. You can prove that the orthocenter, centroid, and circumcenter of any triangle are concurrent. You can prove that. You just need one afternoon of free time with you. Very great happiness with dealing with x1, y1, x2, y2, x3, y3. Rigorously writing down all formulae and establishing that yeah, this works. And so, but that's taking all the joy out of geometry and sticking it into saying I will do it only algebraically. And sometimes when you learn more and more coordinate geometry, we get suckered into the algebra part of it. And I want you guys to say, hey, algebra is fun, but I want to see this. I want to see how the graph looks like. That is really the ball game. I hope somewhere on this discussion you said to see the diagram. Very important. Have fun. I had a lot of fun doing this. Hope you guys enjoyed it and learned something instantly as well. I look forward to catching up with you guys soon. And best wishes for your exam. Ciao. Oh, nice, just a chat. I want to do a musical note for an assignment. Brilliant. Appoint one vertex to the origin, makes life easier, I guess. Lovely. One vertex is origin, another line on the x-axis. Third one being variant. Yeah, much easier. Lovely. Any shape can be translated parallelly throughout the plane without losing any consistency. Correct. Brilliant. Shaksham says, good night. Good night indeed. Good night to all of you and best wishes for you.